In this video, we are going to discuss the conversion of flip-flops. That means if you have a particular flip-flop, how we can obtain other flip-flop function using that particular flip-flop. For example, in this, first we are considering the SR flip-flop. If you have SR flip-flop, how can you obtain the JK flip-flop function using SR flip-flop? So first, we have to find out the conversion table. Now, how this conversion table is written. That is the first for JK we have two inputs J and K. Now QP is the present state and QP plus 1 is the next state, and SR input that is S and R. So first suppose if you are having 0 0 as the input, now present state is 0. What will be the next state when you apply the clock pulse? That will be 0 because we are applying 0 0 at the JK input. That means the output will not change. Okay. Now for this particular output change, that is from present state 0 to next state 0. If you want that output change, what should be the input that we have to apply across the SR input? That is the 0x. This you can obtain from the excitation table of your SR flip-flop. Similarly, you can take another case. So 0 1, that is another combination. So for if input J is 0, K is 1, and present state is 0. And if you want what will be the next state when you apply 0 1? J is 0, K is 1. That means that is a reset condition. So when you apply the clock pulse, the next state will be 0. So if you want to have a state change from 0 to 0, you have to apply SRS 0x. So similarly, you can obtain the other input across SR from this table. Now from this table, we can obtain the expression for S and R using CAMAP. So first we can draw the CAMAP for the S. Here the inputs are J, K and Qn. So combinations are 0 0, 0 1, 1 1, 1 0. Qn can have a value 0 or 1. So from this table, when Jk is 0 0 and Qn is 0, S should be 0. Then here it is X, here it is 0, 0, and this one is 1, this one is X, this one is 1, and this one is 0. Now if you obtain the expression, so this is 0. If you are combining ones to obtain SOP, these ones are grouped together, so you will get the expression for S is equal to, here J equal to 1, so J, K is 1 and 0, so that variable get removed, and Qn is 0, so Qn complement. So that is the expression for S. Similarly, you can obtain the expression for R. So for R, you can draw the CAMAP. So JK, Qn. JK have 0 0, 0 1, 1 1, and 1 0 as the input. Qn have can have 0 or 1. Now for R is X 0, X 1, 0 0, 0 1. Now if you group the ones, you will get R is equal to, for this group J is 0 and 1, so that variable gets removed. K is 1, so K, Qn is 1, so Qn. So we have the expression for S is equal to S and R. S is equal to JQn complement, R is equal to KQn. So based on this, we can draw the logic diagram. So we obtained S is equal to J Qn complement and R is equal to K Qn. So here we have Q that is taken here, so this is Qn. This Qn complement is taken here, this is Qn complement. So this will be J Qn complement, this is K Qn. So this is the J and K input. If you use two AND gates, you can have JQN complement and KQN. If you give this as the input of your SR flip-flop, this SR flip-flop output will be equivalent to that of JK flip-flop. Next, we can take a JK flip-flop to SR flip-flop. So if you have JK flip-flop, how can we convert that into a SR flip-flop? So similar to the previous case, here also you have to obtain the conversion table. Here the inputs the required one is SR function. So that and present state, that is the input variables, and Qn plus 1, that is the next state that you require. And what should be the input to obtain that particular combinations of the output. That is based on that we can decide the JK input from the excitation table. Here we know that SR flip-flop, this 1-1 condition, it is an invalid combination. So that is taken as the don't care conditions. Okay, so first we can obtain the expression for J. So J we can have input as S, R and QP. So SR you can have 0, 0, 0, 1, 1, 1 and 1, 0. This is 0 and this is 1. Now these are the inputs, that is corresponding J values. This is 0, this is X, this is 0, this is X, and this is 1, this is X. These are the don't care conditions. So these two are X, X. So if you group it, you will get J is equal to, so in this group S is 1, R is 1 and 0, that get removed, and QP is 1 and 0, that also get removed. Similarly, you can have the expression for K. So here you can take SR and here you can take QP. So 0, 0, 0, 1, 1, 1 and 1, 0. This is 0 and this is 1. So the input combinations of X, this is 0, X0, X1, X0 and this two are XX. Now if we group it, you can get the expression as, for this group S is 0 and 1, R is 1, so K is equal to R, and QB is 0 and 1, so that also get removed. So we obtain the expression J is equal to S and K is equal to R. So you can have the SR flip-flop function using JK flip-flop if you apply the S and R input as J and K. So this is the logic diagram. So we are applying S to the J terminal and R to the K terminal. Then it will function as a SR flip-flop. The next is how can we convert SR flip-flop to D flip-flop. So here we have to convert the SR flip-flop. SR flip-flop is the available one, and D is the required one. So for D input we can obtain the conversion table. So D is the input, QP is the present state, QP plus 1 is the next state required. So for these two combinations, what are the SR input we have to apply, that is obtained, and from the CAM map we can obtain the expression for S and R. So first we can take S. For S, the inputs are D and QP. So D can have 0 or 1, QP can have 0 or 1. Now if D is 0 and QP is 0, S is 0, this is 0, this is 1 and this is X. So if you group it, you will get S is equal to, that is D. Now similarly you can obtain the expression for R. Here D, this is QP, 0 or 1, 0 or 1, this is X, 1, 0, 0. So if we group it, you'll get D is, sorry, R is equal to, in this group, it is D complement. So S is equal to D and R is equal to D complement. So you have to use D input is directly given to the S flip-flop, and for R terminal it is given through a NOT gate. So this is the conversion of SR flip-flop to D flip-flop. Next is how we can obtain SR flip-flop by using D flip-flop. So the input we have is D. So what is the input that you have to give to obtain the SR function using D flip-flop? So again we have to obtain the conversion table. So here we have three input variable S, R and QP. These are the three input variable which will decide QP plus 1. That is the final output. So to obtain QP plus 1 from QP, what are the D input that you have to give? That is obtained from the excitation table. So for SRQP, this is a 3-bit, so you can have 8 combinations. So for this 8 combinations, what are the QP plus 1? So that is written here. Then for this QP to QP plus 1 change, what is the D input? That is written here. Now here you can see that we are taking these two as invalid because this 1-1 condition is an invalid condition for SR flip-flops. So for that two case, we are taking your D input as don't care. So you can obtain the expression using K-map. So first we can obtain the expression for D as a function of S, R and QP. SR you can have the combination 0, 0, 0, 1, 1, 1 and 1, 0. This is 0 and this is 1. This is a 3 variable K-map. So the output, it is 0, this is 1, this is 0, this is 0, this is 1 and this is 1, this is X and this is X. Now you can group. So these 4 can be grouped as one group, and second group can have this one. So if you write the expression D is equal to, for this it is S is 1, so S, R is 1 and 0, that variable get removed, and QP is 0 and 1, that variable also get removed, plus this for this group S is 0 and 1, so S get removed, R is 0, so R complement, then Q is 1, so Q. So this is the expression for D. D is equal to S plus R complement Q. So the expression obtained is D is equal to S plus R complement Q. So based on this, you can draw the logic diagram. So here you can see that this is the S input, this is the R input. So here you will get R complement at the output of NOT gate. Here this input is QP. So the output of this one will be QP into R complement. Now this is S, this is R complement QP, so S plus R complement QP will be a pair at the D input. So when you give this as the input of D flip-flop, you will get output as similar to that of an SR flip-flop. Similar to the previous conversion, we can here JK flip-flop to T flip-flop is shown here. So conversion table and a corresponding K map, and from this J is obtained as T, K is obtained as again T. So J and K is given as combined together as T. So this will function as a T flip-flop. Similarly, JK flip-flop to D flip-flop, how you can obtain a D function using JK. So again, the conversion table, then the corresponding K map, and obtain the expression J is equal to D and K is equal to D complement. Now based on that logic diagram I can draw. So these are the conversion. So here the conversion of D flip-flop to JK flip-flop is shown. So again the conversion table is obtained. From that K-map is obtained. Now from the K-map the expression and logic diagram is obtained.